So guys, as we were saying in the previous video, the idea is that we will eventually start building integrals from a spatial and physical object. Therefore, we need to choose a variety of different shapes and different objects to see what we can do with the mass differential. This is an example that is slightly more challenging than the previous one. Please pay attention. Hello everyone. Continuing with these integral building ideas, I want to discuss here the mass differential for a thin circular hoop of total mass m and radius r. You will see that the ideas are very similar to the ones discussed in the previous video, with some specific characteristics for this case. We're talking about a very thin circular hoop, so we might consider that this is like a one-dimensional object that is bent around in a circle in such a way that the radius is capital R over here, and since we are talking about an infinitesimal element, a very small element of mass for this object, you could take it over here. Of course, that can be any place around the hoop, and this differential of mass is dm. Now, because this has some length, that length is going to be eventually considered as a piece of an arc, an infinitesimally short arc of length ds, where s represents the arc length in any case. Now, since this is a one-dimensional analysis, we still want to talk about linear density. That linear density, as usual, is mass per unit of length, but since this is a circumference, we're talking about mass divided by the formula 2 pi times the radius. We still want to use the symbol lambda for linear density, and the important part is that because the density is uniform around the hoop, then this is also equal to the infinitesimally small mass dm over the infinitesimally short arc length ds, which means that the mass differential dm is equal to the ratio mass over 2 pi times the radius times ds. If we consider then any function that we need to integrate relative to the mass differential dm, we want to do this around the hoop, then the way to convert that into an integrable symbology is to have the function times the ratio mass over 2 pi times the radius times ds. And the whole idea is that if you start out at one point on the hoop and go around all the way to the end, then this starts with an s equal to 0 and ends with an s equal to the whole circumference, 2 pi times the radius. So this is equal to the integral from 0 to 2 pi r of the function times the ratio times ds. But because the mass and 2 pi r are constants, you can very well take them out of the integral and convert this into mass over 2 pi times the radius integral of your function from 0 to 2 pi r times ds. Now we can go a little further than that. If we take this as amplification of a little part of your arc, and you consider this to be the mass differential dm with arc length ds, say that this is the center of your circle. According to the relationship defined by radian measure, arc length is equal to radius times angle measured in radians, then you could say that this angle, which is arguably very small, let's call it d theta, determines this arc in exactly the same way. ds is equal to the radius of this hoop, which is capital R, times d theta. If you do that, then this integral changes a little bit. You can also convert it as the integral of this function times mass over 2 pi times the radius times the radius times d theta. Since you have converted this to the angle as a variable, then that variable goes around the whole circle, which means that theta starts out as a value of 0 and ends with a value of 2 pi radians. Simplifying this a little bit, you can convert it to mass over 2 pi, integral of 0 to 2 pi of the function times d theta, because the radius cancels out. So these are two ways in which you can take the integral of any function around the hoop.